Okay, so hello everyone. Welcome to the lecture number five. Yes, fifth lecture. I think so. Yeah. So last week as usual, we didn't do much, right? But it was high intensity. So we talked about probability spaces, some interpretations of probabilities, and in particular, we discussed which interpretation of probability most likely would apply to quantum mechanics, to Born rule. The frequentist interpretation, to be concrete, of course, with an asterisk, provided that we can resolve the issue with initialization, which I will try to do at some point, hopefully. But we also noted that there is some weirdness with quantum mechanics, because in classical theories, the different interpretations of probability, they can I think always be like exchanged with each other. So frequentist interpretation can be also like exchanged for bias interpretation, and just the point of view changes a little bit, but it's all applicable. And this the reason for that is like the classical theories have very special form, universal form, and maybe I will talk about it a bit at some point when the time comes. Although I don't guarantee that. But quantum mechanics is different. It's not like classical theories, which is kind of obvious. With classical theories, the other name for them is non-quantum theories, I guess. So quantum mechanics is different. So there is some issues or mysteries, let's say, with interpretation of probability, because quantum mechanics comes in and throws in some disruption here, and it's not clear how to resolve it. But anyway, and this is the place we got to. We talked about a little bit about measure theory as well, some extra stuff. It's not super relevant for this our problems at the moment. So so let me carry on from this point with the program. So we got to this frequentist interpretation of what is the meaning behind Born probability, that this is like a relative frequency. If you consider like an infinitely long trial of experiments where we apply the measuring device, reset, apply, reinitialize the system, apply measuring device, and so on. Assuming that we can do it, we know what it means, then this is how you can interpret the Born rule. The other thing that comes with it, it's like, so in probability theory, you can so the probability that something event will occur, this is given like this, but since our experiment or the process we are describing formally with probabilities, it's random. So whenever you do the experiment, you have some, you don't know what will happen exactly. You can just you can say what is the probability that something concrete will happen, but what if you want to like make a prediction, some kind of prediction about any given experiment? What can happen in this experiment? This is where estimators comes in, various kinds of estimators. And one very like popular and important estimator is a so-called expectation value. Let me boot up the tablet. So it's I'm not sure what is the story behind it, but there is certainly some interesting story. Yeah, I am recording. Sorry, I got scared for a second that maybe I didn't press the buttons. The other one's also recording. Okay. They say, I mean some probabilists, that when you take an average of your results in an infinitely long trial, so this huge average of results, that this is the expectation value, and this is a estimator for the result of any given experiment. So this is what they say. I read it as like, okay, so this is basically, when I do an experiment, I expect that the result will fall somewhere around this average value, right? It does not specify completely what will happen, of course. You would have to like higher order estimator, use higher order estimators maybe some dispersion to know how far can your result fall from this average value and so on and so forth. But the expectation value is something that, like first baby steps, and try to do some statistical analysis of your experimental results. So the expectation value is defined the following way. So expectation value, this estimator, it's not like something that's tied fundamental for quantum mechanics. This is like, since we have this probabilistic interpretation, we can use theory of probability. And when you are using theory of probability, you have estimators. Okay, so we're just using tools from different theory to analyze, to make a connection in quantum mechanics. So any classical theories, you can also have estimators and expectation values and stuff like that. For quantum mechanics, there will be some connection with, with Born rule and stuff like that. So just a disclaimer like this. Value, expectation value of observable X, right? Because we are, this is the mode where we interpret observable as a stochastic variable, right? And the formula is, like I said, it's supposedly, this is a, so the notation is E of observable, so capital X, but I will add the condition that it's provided that we have, the state is psi t. And the way it is defined, it's supposedly the trial is infinitely long, so we will have n number of trials goes to infinity. And they say to take an average, which I will like write, so 1 over n, and then sum over k from 1 to n. And the things we are summing, so we'll just describe it in words. So the result xk, so like a value of the result, whatever we get, obtained in trial number k. Okay, so the value in the given run of the experiment. So that would be the definition. But now, since our experiment, there are only a finite number of possible values that we can measure, right? So we can basically group all the cases when we get certain value x, right, and just count them, how many times it happened in this n trials, which basically we can convert our average into weighted average, right? So we can just do it easily. Limes n goes to infinity. So sum over different results. Results, of course, sit in the spectrum of observable, right? So we have value of our result. Now the weight would be number of results x in n trials. and divided by n. But this you can, so number of results we obtained, but this is the same number as here, that's the relative frequency, right? So we get the classic formula. I can just eat the limes. So this just turns into sum over spectrum of observable x times px x psi t, right? Agree? But then we can go further because we have Born formula. So we have here sum x over sx x times psi t px x. So I will just invoke Born rule here. Psi t normalization. But now I can just enter with the sum under the bracket, and I have psi t sum over x p x projectors psi t divided by. But what is this guy? What we recognize here? This is an observable, the operator representation of observable. So we get that expectation value. So this, like the statistical thing, it actually refers to explicitly to this formal representation that we constructed to pack in all the information about measured observable, which is kind of neat, right? When you discover things like that, it's like, oh, so I wasn't just doing random stuff. There is some, there are some connections, which is a nice result. So expectation value is like, yeah.
I think that was a thing. What is k in the top? We wrote down trade k. I guess that was a typo, or in the like a little bit higher.
Let me check. There might be a typo. Okay. So if you each trial of the experiment, let's the first one, the second one, the fourth one, each one has its own. There is some value measured, right? So that would be xk, and you take average of all of them. Okay, this is what I mean here. So there is xk, and many of them will be the same value nominally, the same numerical value, right? So that's why we switch to the weighted average instead. Yeah, and this is kind of nice, but there is something interesting that we can do with this expression, because we learned that the state solution to Schrodinger equation, that it has a very specific form, right? That this guy is an evolution operator, our favorite evolution operator, acting on the initial state, right? So witness what happens when I just write it down explicitly. So some formal manipulations. Some shenanigans. We will play with our formulas. So we can write E x psi t. So if I just write it down explicitly, I will get so bra of the psi, which means that it will be bra of initial state, and the evolution operator we will get a dagger in the back, right? And we have in our observable here in the middle There will be evolution operator here on the other flank, and omega, initial state. And the denominator, t minus t0, h dagger So there are a couple of things that immediately should be, I mean, it's kind of obvious if you are used to it. If you remember, evolution operators are unitary operators, which means that the dagger is a inverse, right? So this is nothing else but identity. Right? They cancel each other out. This is nice. So this normalization factor is a constant, actually, right? The other thing that what you might exploit is that the dagger is an inverse, but it also what it actually does is flips the time to minus time. Let's say, so we can consume the dagger and simply write it like this, just for brevity. And now when we look at this, divided by omega. So it kind of looks like the expectation value is taken on the initial state, this omega, and the evolution operator now has been transferred onto the observable, right? So we started by thinking that this is the state that is evolving. Operator acts on some vectors. But now we're doing some formal trickery, some shenanigans, and we kind of move it, transfer it onto observable, right? So we can make a definition here, t minus t0. Okay, so now the observable is time dependent rather than the state. Okay. So maybe I can even write that this is like an expectation value of x t0 conditioned on the initial state. Maybe I can write it like this. So this looks like some formal trickery, and this is called switching the picture. So this would be a Schrödinger picture when you keep your evolution operators acting on the initial state, and this would be switching here would be a Heisenberg picture where you say, okay, so no longer the states don't evolve; it is the observables that evolve, or the observables evolving. So this is and we, as we can see, we at least in this formula. And it is also, you can imagine this is also true for the Born rule, because it also has this kind of form. It's just a projector stands here instead of full observable. You can do it at will, whenever you wish, right? There's some trickery at this point. So we have our Schrödinger picture. Schrödinger picture. Where you say that your states evolve. It's how usually people want to say the states evolve, and observables are static. And Heisenberg picture, Heisenberg picture. So you say, okay, so the states are fixed, they're static, but observables, operators, are evolving.
So that H is for Hamiltonian in the U.
Yeah.
Okay, yeah, because I thought it's Heisenberg.
No.
Okay, yeah.
We won't be. I mean, basically, we don't need the distinction because, I mean, this is the convention of indices. And besides, we will soon switch to Heisenberg picture exclusively.
So the evolution operator stays the same in both pictures.
Yes, it's the same unit that responsible for dynamics. Where it acts, it's like at, I'm showing here that it's kind of you can switch at will, but
domain is changing, so actually there are two different operators in my opinion. Because one is acting on states and the other is acting on operators. So
formally speaking, so this is evolution operator acts on states. That's fine. We understand what it means more or less. But here it's like it's not really just you. You have to take this sandwich. So this is like so this is actually so you can take this if you want to like see it formally. This is actually a super operator, which maybe you could write it like this. So this is an linear operator acting on operators, right? So it's actually this sandwich is a.
actually just the composition of functions. Like u, x, u, everything still acts on the state.
I mean,
then your u is still consistent, it still acts on states. It's just the way we write it. It's just a function, right? So it's like composition of functions. Like,
I mean,
right? So
formally, yes. We didn't do something illegal here. We just.
no, like when you said it in this way, I just noticed that the domain feels different. So it's not. Yeah, so it's not. It seems that it still acts on the state. It's just now we are looking at it at a composition of function point of view. Heisenberg picture in a way. So yeah.
Yeah. But this is not just formal trickery, because there are real physical consequences of this ability to do this, to switch pictures. Because I mean, I kind of dropped a hint here, but look, this for any Heisenberg picture of an observable for any time is a Hermitian operator. If observable is a Hermitian operator, then its Heisenberg picture is also a Hermitian operator, which we can like easily check. So if you take for some arbitrary tau, and you take a dagger of this bad boy here, so you just put here evolution operators, and you dagger everything. When you dagger it, you have to dagger each operator, but also like reverse the order. So we are getting here this guy. Actually, the x will stay in the middle. Reversing order means that guy in the middle stays in the middle. Minus h dagger, okay. But now this is Hermitian, so this is just x, nothing changed. This we can absorb the dagger. We just have to change the minus tau to tau, right? And this guy, the same thing, minus tau, which is we just restored what we started with. So this is x of tau. So it's Hermitian. If it's Hermitian, the spectral theorem tells us that it has a spectral decomposition. Spec theorem. So x tau, there is x in a spectrum of x tau, eigenvalues, projectors. right? So this is there is a spectral decomposition. As a bonus, we can easily show that actually this spectrum does not depend on tau, the value of tau, which we can do a quick calculation to prove this. So if we take, let's start with the spectral decomposition of the initial, maybe in quotes, initial observable X, the one that we sandwich in. So this guy is an observable, so it has its spectral decomposition with its original spectrum and original projectors, right? And we know also that this decomposition is a solution to this eigen problem for this Hermitian operator X. In other words, we can write that, consult my notes, make sure I'm not missing anything. Yeah, okay. So we can write X minus eigenvalue 1 on X equals 0, right? Because this projector and this eigenvalue, this pair is a solution of eigenproblem, right? So this is 0. But now we take this and we sandwich this. Before I sandwich, maybe let me move around things. So let me take the part with the projector on the right-hand side, and let's leave the part with X on the left-hand side. So I just moved around the things. And now let me sandwich this with Heisenberg. Let me switch to Heisenberg picture, both sides, let's say. So here I get U minus tau H acting on operator X, acting on projector X. Sandwich from the other side. And here X this is a number, so I just get here X U tau X. Okay, nothing illegal happened, hopefully. So this is just here we can recognize that this is a basically Heisenberg picture of this projection operator, right? Agree? This is how we think about this guy. So this is just Px of X tau. Okay. I see being consistent, what goes into subscript and superscript is key here, right? On the other side, we can do like a popular trick that you do with calculations like this. So we can insert in between X and P identity. So we can always do this. But identity, what is identity? Well, one of the forms of identity is U with its inverse. This is like a standard trick, of course. Everyone knows this. But what you get in return when you do this trickery, you get U minus tau H X U tau H and U minus tau H Px X U tau equals X P tau X X, right? And again, we recognize here immediately, this is also the Heisenberg picture of the projector, and this is the Heisenberg picture of observable. Okay? Now, moving stuff around, to the one side, to the left-hand side. So we get x, Heisenberg picture, minus x, 1, px tau x equals 0. Okay? So what's happened here? So for every x from the spectrum of the initial operator, we find operator p, which is a Heisenberg picture of the original projectors, that solves the eigenproblem for operator x tau. Okay, which means that one, we have eigenvalues are the same. Doesn't matter which tau we pick. You know, this is the same as the initial guy. So this is as advertised. S x tau equals s x. This is supposed to be math and b. Math bb, sorry, s. I don't know how to write it. Maybe it should be something like. It will always look like shit. You know, it has to look like shit. I don't know how to write it nice.
One question. So if I remember, you need to have that x minus x identity commute with the projector, right? You need to have one more equation, right? Because you need to have the flipped condition also equal to 0. Not one is sufficient. If I remember from your initial definition of eigenvalue equation.
Well, I can. So this is an equation.
Like, so you started from x minus
yeah.
I was asking, but that does that imply the other one, like the flipped one, is also 0? Because I think you need both of them simultaneously, right? P into x minus, you need to simultaneously solve that, right?
Yeah. I mean, I could write the other one as well here, and it just repeat the steps, and it will be.
Okay. So in principle, you should account for that also. Right?
Yeah. Okay. I should. So what he's saying is that we should also have this. Yeah. That it commutes equals 0, right? But again, we were starting from this and sandwiching identity, we'll get the same. So imagine in your head that we did it and we got what we supposed to get. So we know. So okay, the spectrum is the same as advertised, and we can also these operators here. I mean, they are solution to the eigenproblem, so they have to be the orthogonal, full set of orthogonal projectors. But we can actually check this explicitly, that those Heisenberg picture of projector is a projector itself. And the full set is orthogonal to each other, and so on and so forth. And we can check this explicitly if we wish. Orthogonality. Because if I take tau x, although maybe it is actually helpful to look at this x prime. And what is key here, that this has to be the equal time projectors. Okay, this won't work if I take different times. Okay, and I just go, explicitly write down the evolution operators. X, and tau h minus tau h. Hopefully you already see what will happen here, right? Tau h, right? Because they are neighboring. The neighboring operators always, one is inverse of the other. Of course, if tau is the same, right? If tau would be different, this would not reduce to identity. And once it reduces to identity, then those two guys meet, and you can use the orthogonality condition for the original projectors, x prime px x, right? And it's sandwiched with evolution operators, so we switch to Heisenberg picture, and we get our and we get what we came here for. So they are orthogonal. Similar way, using similar moves, you can show completeness, right, when you sum over of x's. So allow me to skip the algebra, it's easy stuff. So we found out that, okay, so the Heisenberg picture of the observable is an Hermitian operator. It has a spectral decomposition. Its spectrum is actually the same no matter the time. It's time invariant. And we also found the complete set of orthogonal projectors, which are the projectors of the original, the initial observable, but viewed in Heisenberg picture. In other words, to summarize this excursion here, this Heisenberg picture of the observable, this x tau, is an observable itself, okay? Therefore, in principle, there should exist an x tau device that can measure this observable, okay? Since it is an observable, so it should be measurable. There should be a way to build a device that does it. And now, given that the Born rule has a form where you can switch between Schrödinger picture and Heisenberg picture. So this is like the result is the same no matter in which picture you look at this stuff. We come to the conclusion that it is indistinguishable. I mean, whenever you measure observable x at time t, okay, so you measure x, so you apply x device at time t, okay. The result is indistinguishable from the situation where you measure, let's say, x t minus t0 device at time t0, at the initial time. So to make it more explicit, if you write px x on psi t, okay, the Born rule, so psi t px x, this equals to omega t minus t0 x. So we just switch to the Heisenberg picture, right? As we show that we can. But this we just found out. This is also the same as saying that we are measuring observable t minus t0 at time 0, at time t0, initial time. Meaning that this is p t minus t0 x at omega, right? So it's indistinguishable whether you are there's initialization, you wait for time t minus t0 and you measure observable x, or you don't wait at all, you just measure the device with x t minus t0 device. In other words, in principle, it's always possible in this setting, in this context described by Born rule, to compensate for the dynamics with some adjustment to measuring devices. So you can explain any experimental result with just there's some interplay between measuring devices and the initial state, right? And measuring devices is something we control as observers, right? So we can, we can always pick a measuring device so that there is no passage of time at any point. Okay, it's indistinguishable. Whether you wait or not, you don't wait. So because you can do this, because you can compensate for the passage of time, for the dynamics, so this is like, I call this a quantum statics regime, okay? Because there is this ability in principle that you can eliminate the dynamical effects of the system by adjusting the measuring device, okay? Quantum statics, as opposed to quantum dynamics. This does not mean that passage of time and dynamics is like irrelevant. It has no meaning, because as you can see, this compensation for passage of time, it's like something you have to engage with, on purpose when you are an observer, where you have to adjust the measuring devices to eliminate the time, or maybe to simulate that there was more time that passed or shorter amount of time, right? You have to adjust your measuring devices to do it. But in principle, if you wanted to, you can eliminate it completely. And if you eliminate passage of time from your description, you are also eliminating the evolution operator, or the Hamiltonian stops being relevant. Which means that you basically have a regime, if you're working this quantum statics regime, where the identity of the system you are working on is like erased, it's irrelevant. Because if Hamiltonian doesn't matter, Hamiltonian is the thing that identifies this system. This is what distinguishes one system from the other, right? So we can completely anonymize your description in this way. And now you might ask, why would anyone want to do such a thing? Because isn't the point of physical theory is to describe, or maybe even explain how systems behave, right? And how can you do that when you erase the identity of the physical system you are describing? That sounds like insanity, right? It's completely counterintuitive. However, there are legitimate reasons, even though this is counterintuitive, there are legitimate reasons for doing such a thing. And a prominent example of a subfield of quantum physics is a quantum information theory, right? Because when you work in this kind of quantum statics regime, where you can imagine that it's possible to eliminate the identity of the system, you can talk about platform independent description, right? So if your goal is to describe or devise some quantum computer that does runs some algorithms or programs and stuff like that, it's you want to work in the regime that allows you to not bother with thinking about some details of hardware implementation, right? Like in classical computer science. You rather think about an abstract Turing machine. You don't want to think about, currents and transistors and stuff like that, the concrete implementation of hardware implementation, right? You don't want to think about, okay, how many milliseconds it will take for the current, for electrons to pass to this transistor and for it to switch and stuff like that. You just want, okay, there is some circuit, and I don't want to, some engineers figure out how it works. You just have some standard effects, and I would just, apply transformations in an abstract way. I just, sequence of some transformations to the state of my computer, my memory, or whatever. So therefore, this quantum statics regime is like a perfect fit for this kind of approach, right? So that's why quantum information loves this kind of thing. because it allows it to mimic classical computer science essentially. So yeah, exactly. So in this kind of approach, you don't think about dynamics of the system. That there are states or whatever that changes in time according to some dynamical laws of the particular physical system implementing your computer. You just transform states with some abstract transformations. Those transformations might be like the genesis of those transformations, might be some actual evolution operator in some predefined tick of time or something like that. But you just don't care about it. This is for engineers to figure out. You just want your gates, to implement your circuits. And once you do such a thing, then this lesson from the Born rule, it's like you are compensating for the dynamics. Dynamics no longer there. You have just some transformations, which we imagine that we, the controllers, apply to the system. So in that case, what is left in our description that's like relevant is the state, right? In Born rule, if I can, this projector is something that I, as an observer, apply. If I control through this application flow of time and all the dynamics and everything, I just compensate, do whatever I want, then the only thing that remains is this initial state, right? So in the sense, in this context, this regime of quantum statics, the state is like the master object of the formalism, right? This is the only thing that explains all the measurement results, all the observations, right? The state is the only thing that remains. And this is why quantum information and all the adjacent subfields, they focus solely on states, right? This is where things like entanglement come in, discord, non-locality, and stuff like that. So some way of like analyzing and categorizing some geometric properties of the initial state. There is like the dynamics is basically absent, right, in quantum information. When you think about some, evolution, is through these circuits, that there are some abstract transformations that take state to the other state, to the other state, to the other state, and this is like the, my gates do the computation or whatever. But there is no dynamics, there are no Hamiltonians, right? Because you want to have this platform-independent description, right? So you make quantum mechanics into the theory about states.
It's an ideal picture because you think that your system is isolated from noise.
Well, if it's not, then you have your standard gates that simulate the the decoherence or stuff like that. Although, but if you still want to, since you want to remain this static regime, you cannot allow all possible, decoherence, not all possible kinds of noise. You want to specific kinds of noise that won't kick you out of the of this regime, right? So it's kind of that's why everything has to be for those who know Markovian and stuff like that. So that you can be kept inside this statics regime. So what else? Master object, I said that. It explains things. Yeah, contents. Yeah, okay. No. All right. Yeah, okay. So this is a quantum statics. This is why I invented this name, say, because this observation that you can eliminate passage of time, and by doing so, we can also eliminate the identity of the system. So we have platform-independent stuff, and when you do that, the state is all that there is to your description. So you can focus on it, and all the answers will be there. Okay, the master object of the theory. However, this thing will not. This is not like whole quantum physics. Okay, this is very specific. This is a very specific context where this works. In the following stuff, I will want to show you that in broader context, or in majority of contexts, this cannot be done. This elimination of dynamics cannot be done. And then the dynamics, the dynamical laws, the evolution operators will be like the king, the thing that is like actually comes in and brings in some physics, some effects, right? And then, and as a consequence, the role of the state, the initial state omega, will like get smaller and smaller and smaller and smaller, and to like maybe spoil a little bit what will happen later. At some point, we will come to the conclusion that, you know what, if I'm not doing quantum statics specifically, I actually don't need states anymore. Okay. So that will be the trajectory. But for now, let's take a break. Yeah, let's a couple minutes of break. Okay, so let's continue. So I kind of try to introduce the idea of statics. So before we get to real dynamics, the opposite of statics, the path leads through the topic of initialization. Okay, so then the next step in our constructions will be section, in my notes is 1.4, and it's entitled initial condition. And to talk about initial condition, okay, no errors. So I have here a mathematical aside, traditionally. Okay. So, you know, I have here a like crash course on matrices and trace operation. And like, I kind of promise that I will leave no stone unturned, but maybe I can leave some stones unturned, okay, because I'm already lagging so much behind, and now explaining what matrices are and what traces, maybe just you will be bored too much, right? And those who want, of course, it's written down. If I said anything, it would be basically repeating what's written here, right? So maybe just points of interest in this note, maybe notation convention, right? So what kind of notation I will be using? So I figured that matrices, because matrix depends on which basis you use to calculate your matrix elements. So I take an operator A. If it has hat, right, this is an operator, so like, you know, like abstract thing. But if it's in brackets, square brackets, it's a matrix. And the index, if it's like one of the in the math BB font, that means it's a matrix in the basis B. Okay, which basis B, some orthonormal basis that we chose for ourselves. And also then, so this is a table filled with elements, matrix elements, and matrix elements also brackets, square brackets, but with two indices, right? And indices corresponds to which elements of the basis we are addressing here. So the matrix element, to calculate it, you just take a bracket between the basis elements. Okay, hopefully nothing, no more explanations needed here for this audience. Trace, important operation. Once you have some base, you pick the basis, and you have matrix elements of your operator. The trace is defined as a sum of all the diagonal elements of the matrix. So you basically sum all those guys on the diagonal of this table. And the mysterious thing about trace is that although it's defined, it involves some explicitly needs matrix elements, so need bases, right? But as it turns out, it's independent of the choice of the basis. It's a kind of mysterious thing. So this is like a property of an operator, abstract operator, right? But to compute it, you actually need bases, you need matrices. I don't know what this means, but this is kind of like mysterious to me. Okay, it's like, is there some alternative formula for trace that doesn't use the? I don't think so, right? It has to use matrix elements. I mean, if you have like infinite dimensional Hilbert spaces, then there is a difference. Yeah, but it's
Supremum, or because now you can extend that summation to, like, I don't know, supremum of that's expectation value.
It's somehow connected with spectrum for sure, because since, so I show here that it's so this is trace computed for this basis B that we chose, but if you choose some different basis B prime and you just repeat the calculations here, you will discover that it's also the sum of all the diagonal elements of the matrix in B prime. So it's in this sense it's independent. A question?
But if you are starting with spectrum, then you will only be able to talk the trace about operators which have a spectrum.
Yes, so I'm getting to that. So in particular, so I can choose any basis. So what if I chose basis made out of eigenstates, eigenvectors of my matrix? This is a special, deeply connected basis that is like intimately connected with an operator. So I choose here with the notation that we introduced previously, the basis, eigenbasis, let's call it, of our operator A, and I calculate the trace using the same formula. I'm just using my eigenstates. Thank you. But it's in eigenbasis, the matrix of the operator in eigenbasis is only diagonal. There is nothing else, only diagonal, and diagonal is occupied by eigenvalues. So the trace just turns into a sum of all the eigenvalues. So I think this is, if you have like infinite spaces, you have some operators, bounded, unbounded operators, who knows? But as long as they have spectrum, maybe this is how you can, like, integral over spectrum. Yeah. That's maybe like a basis independent definition of trace that works even in some pathological Hilbert spaces. But I don't know. I'm not sure about that. But this is like very, very weird.
Earlier I said you can use supremum, but that would be the norm of the operator, so you cannot use that. Yeah, so it's my mistake. Yeah. But
maybe supremum of some cover of spec. I don't know. There might be some.
Trace is a number, right? So you probably end up using some real number property from sets. There is no other way you can do that.
So maybe some measure. I don't know, man. But to calculate for our purposes finite dimensions. Okay, so just pick a basis and calculate all the stuff on the diagonal, or this connection with eigenvectors. It's also a sum of eigenvalues of an operator. So this is kind of cute. Okay, this is trace. And trace has, so I have here assignment to prove that trace has this cyclic property. Okay, so you can basically, let me try. Let's go back here. So cyclic prop. There is no like, we have orthogonality. There's like one name for something, but this cyclic property, they all, in Wikipedia, in books, it's cyclic property. So there's no like cyclicity or something like that, which is disappointing. It's like cyclic property of trace. It's like, what kind of name is that? But it's generally, so if you imagine you have like some number of operators like this, so now you can like move them, and it's like in it's like on the torus. I don't know. It's like you go to the edge of the map and you come back from the, like in civilization, right? You go to the edge and you come back on the other side. So you can just cycle those guys. So Z, A, B, C. What's before Z? X, Y, Y. Okay, Y. And you can like you cannot move. I cannot like B with A, exchange B with A. To do this, I have to like go to the edge of the map and come back. Cyclic property. Yeah, so you can prove it by calculation, assignments there. Okay, so that went fast. It wasn't super fast, but still. But now I trapped myself because now I have, I assume I will be talking about it, and now I will rush through my notes I have printed out. So let's see. Okay, so having said that, so we have trace. All this stuff was to like introduce trace for those who don't know. And now I want to make initial condition. I want to make certain observation. Because we had, at the moment, we think initial condition for us is this initial state from the Schrödinger equation. That is this omega. Okay, this is what we think about initial condition at the moment. However, it is always possible. So this is some ket, arbitrarily picked ket, but we can always formally what you can do, you can identify this ket with an eigen ket of some observable. It can be one of the eigenstates of some operator. This is something you can always do. And to show that this is possible, we can construct such an observable. Okay, so observable associated with this omega. And the construction is pretty simple. So we start by defining a projector, and we construct a projection operator onto omega with the standard formula with ket bra. Okay, like in Gram-Schmidt and those other things we talked about. So that would be one projector, rank 1 projector for those who know what's up. And then to have a complete set of orthogonal projectors, we need something more. But it's quite easy to construct an orthogonal projector to this one. Just take a projection on orthogonal subspace to this one vector, which is easily orthogonal to omega. That's my symbol. And this guy would be just 1 minus p omega. Okay? So 1 minus ket bra, just to be explicit. Those two guys actually form a full, complete set of orthogonal projectors, which we can test explicitly. So I am constructing now observable O. Observable associated with this omega. Okay. So my claim is that the set of projectors for O can be, it's already fulfilled when we take those two guys. So to prove this, I can do just straightforward calculations. So first I have to show orthogonality, So, of course, p omega square, we know it is by construction that it is projector, so that's fine. So what about this other guy? Is it really a projector? Let's calculate the square of this guy. So 1 minus p omega square. So that would be 1 square minus 1 times p omega minus p omega 1 plus p omega square. So it's 1 minus 2 p omega. This is those two terms. P square, it is a projector, so its square is just plus p omega, right? And we get 1 minus p omega, which is p orthogonal. So this is a projector. Very nice. Are they orthogonal? Well, we just have to calculate the one after the other. So first this, p omega minus omega, so p omega minus p omega squared, which is p omega minus p omega, which is 0, orthogonal, nice. Completeness, I mean, it's kind of obvious, right? I add them together, only the identity will remain. So this is like a easy construction. So that would be a projectors. What about the spectrum? Okay, we will construct the observable. It also has to have spectrum. So we need two numbers. So let's pick SO. Let's just pick it 0 and 1. Why not? The simplest thing we can do. With the assignment that PO0, let it be P omega. Okay. So this, and the other one, 0, 1, would be this guy. Assignment. I can do whatever I want. This will be an observable with an operator representation of O. So it would be sum over omega unit spectrum O omega PO omega, which in our case is quite easy because it's 0 times P omega plus 1 times 1 minus P omega, which reduces to this form. This is a proper observable. Okay, maybe it's kind of weird, but in principle it works. And in principle, there's a device that can measure it. And its results it will display to us will be 0 or 1 in this corresponding way. We can also construct a eigenbasis for this observable, right? Eigenbasis of O. So for one, it will contain the omega, the ket omega, on which we project with the first projector. Omega. We want to have an orthonormal basis, so we normalize it. Okay, we normalize our basis, and there will be whole. So this would be this corresponds to omega 0, or eigenvalue omega 0, and we will have to omega 1. It's highly degenerate, right? So we will have here a bunch of one bunch of kets. Oh, this is the notation I introduced previously. Okay, so O because observable, 1 because eigenvalue 1, and indices enumerating the orthogonal kets in this eigen subspace. And there will be d minus 1 such states because this is how we construct highly degenerate eigenvalue. So we did it. Should be proud of ourselves. And now, having said that, let us, just for shits and giggles, let's calculate the following trace. So I want to have trace, okay? And inside this trace, I will put two projection operators, p, t, x, of some associated with some observable x at time t, Heisenberg picture. And the other projector will be O, T0, 0, TO, 0. Should I do this to indicate zeros? Nah, everyone knows what's going on. So this kind of trace, that's my proposition to calculate, an exercise. So to calculate this, let's pick our basis, orthonormal basis. This will be easy to do with this. But first, let's do some shenanigans. So so minus t. So Heisenberg picture in explicitly. Th. Okay. If this is what I want to do, then I will do it. Heisenberg picture for the other guy. 0. T0H. Okay. And now let's do cyclic property, cyclicity of trace. Because here we have two evolution operators next to each other, different times, so they won't cancel, but the composition rule applies. So the times will just add up. T minus T0. Okay. Now we use cyclic property to move this guy to here. Okay, so that they meet again. Two evolution operators meet again. And we get U, T, 0 minus T, H, Px, X, U, H, T minus T0. And here our projector we just introduced, which means this is, what do we have here? Trace. Heisenberg picture of Px in a like shifted time. And this guy. And now to actually compute the trace, let's pick the basis, because we have to do that, right? Like we discussed. But we have our eigenbasis of O, which will be very convenient in this case. So let's do this. So we calculate the diagonal matrix elements of this product of operators between cats and brass taken from this set. So there will be like a big sum over these degenerate states, and there will be one special term coming from this guy here. Okay. So let me write here the sum over k going from 1 to d minus 1, O1 k px t minus t0 x. And here, let me put here explicitly p omega. Okay. And the last guy will be omega x p omega was divided by square root of bracket omega squared. So just omega. And now this guy, this is just because this is a projector onto ket omega, so it does nothing. So this just changes nothing. It's already projected. But those guys, these are orthogonal to omega, so this projector just spits out 0. Okay. So the only thing we are left with is omega px t minus t0 x omega divided by omega. And lo and behold, what do we have here? Okay. Well, this is either this omega or, like we discussed previously, x psi t, right? This is a Born rule, the alternative form for the Born rule. Now let me, so because I didn't talk about the trace in matrix elements, I catch up with the end of my printed notes, so I have to go to my reservoir of printed notes and take out some out-of-date notes. Yeah. And now, since this, I mean, this calculation was trace, we chose the basis, but this is basis independent, right? We picked this basis because it was easy. We picked another one; it would be the same, must be the same result anyway. So, so that's why we have this general relation, right? So we have a pxx, this probability, of course, equals the static probability. Static probability equals this trace here, x t minus t0 x po 0 equals trace pxt x various equivalent forms zero. Okay. And now, what is this trace formula then? Okay, it's like, does it have a meaning outside of Born rule? And yes, it does. this trace formula is it's typically it's just interpreted as a conditional probability. Okay, so this trace formula is interpreted as a conditional probability. We will talk more about conditional probabilities in next lecture. Okay, for now I just you probably heard about conditional probabilities.
Yes or no question. So the partial trace can also be interpreted like this? Yes or no? I don't want to deviate from.
I mean, partial trace is not like it's not a real thing.
But still mathematically valid.
I mean, the partial trace appears when you consider an observable that's like in the form of some operator times 1 in some subspace. Then the trace can be reduced to partial trace. So get there from construct your answer from this observation. Because like on its own, partial trace is not a thing, not physically meaningful thing. So conditional probability, so let me write it like this. X, observable X, conditioned observable Y, T2, conditioned by T1, X, condition Y, okay? And the trace formula, so Px T2X, Py T1Y divided by trace Py T1Y. Okay, this is for properly normalize everything. I mean, this is like treat it as a part of the definition.
So let me, because it's like a lot of not the subscriptions over here. So X and Y are two observables. Right.
Yeah, so what, conditional probability, but what are the conditions? So this is a conditional probability for the following chain of events. So this is a probability that X device deployed at time t2, okay, will measure X given that Y device deployed at T1, we're assuming T1 is smaller, and T2 is later. We don't want to have, we don't need time travel, yields Y, okay? So this, yeah.
The fact that you just said now, T1, T2, but why is it not evident in the expression that we write? Did we assume it somewhere? It should be evident from the math that T2 should be larger, or like somewhere in the steps it should be used, right? Physically valid.
If you write, I mean, the formula is valid, but the interpretation is not interpreted. Okay.
But that seems a bit off. Like the math is not knowing about that T1, T2.
I mean, there is no symmetry between 1 and 2, even in this formula, unless this trace in the denominator is 1, right? Which is possible. Actually, here in this case, this trace is 1 because this is a rank 1 operator. That way, we didn't have to put it in. So it's actually, because of cyclicity of trace, you can imagine that you can just switch the places. So there is like illusionary symmetry. It's not really symmetry. Okay, but the formula, you can write down this formula. You can cycle it. Okay, but there will be no. You don't need to have interpretation for that, and you actually don't have it. This you can like make out of it some because this is a conditional. So x under the condition y, right? But you can bias law that allows you to infer. I need to get x under the condition x. But this, which you would imagine that it would involve this cycling here, those two guys. But this is true that this formula would be like preserved, would be used, but the interpretation would be different because then it would be inference, like Bayesian inference from measurement results, not like inversion of arrow of time or something like that. So we for the arrow of time going from past to future, we have an interpretation, like I said, this conditional probability that measurement result at time t2, provided that at time t1, earlier time, it was result y. This is our interpretation for this canonical arrow of time, causal arrow of time. The other one is just a formula. We don't need to interpret it. And if we want to interpret it, then this would be part of like inference. So what would have to be measured before to get results? You know, it's like Bayesian inference, but no travel in time is necessary.
Yeah. My question was not about the interpretations. Like, why isn't that math reflecting our our causality, for example, right? Yes, but like,
there is answer.
So that's what. So it has to come something from the dynamics, I would guess.
You don't see it here because this is too simple of a case. Because this is like condition and measurement and end, and we finish our experiment. But this is only very simple, the simplest kind of experiment you can do. We will see that when you add, let's say, more measurements, it will be clear that there is like the order very much is unmovable, let's say. The cyclicity doesn't change anything. But baby steps. But yeah, this kind of things are like, of course, coming up to you and begs the answer, right? This kind of thing. But let us talk about this philosophically. What's happening here? Okay, this kind of so this is a conditional probability which has like so it describes this kind of association between there was a measurement at time t1, we did it, there was some result, and then we did another measurement, okay, and this gives us all the probabilities how it works. So and the Born rule, we saw that we can like Born rule can be reinterpreted through this lens, right? That we, instead of talking about some initial state, and then measurement happens in some time, absolute time t, we say that, no, it's actually, there was like a preparatory, so we like synchronize two measurements, instead of like looking for some measurement on some absolutely set state of the system. Instead, our experiment is an association, correlation between two measurements that that happened in were deployed devices that were deployed at some specific time with a delay between them set by us. And this is actually key insight because this resolves basically, not fully, but it's a step towards resolution of the problem of initialization. How do you initialize your experiment, right? Previously, when we're still using states, we had this this silent assumption that there is a every system can be assigned state that we know of from some source other than measurements. You have to be aware of this state, this psi t. You have to be aware of it somehow. We could argue that, let's say that we know what are the dynamical laws of our system, the Hamiltonian, the revolution operator. So we actually just need to know, deduce somehow just like the value of omega. That's some initial, the state at some initial time before the measurement happens, and from there we could just evolve it with unitary this evolution operator to the time we need it, right? But still, even if we could do this, which would require another silent assumption that there is like there is an absolute time, right? So all the clocks are always synchronized with some absolute flow of time, which is a big assumption. Okay, not really acceptable in reality. Even if we assume that this absolute time, there's no issues with synchronization, we still don't have any means for identifying this initial state of the system. Okay, and this shows us this conditional probability construction resolves this issue, but the resolution is not by giving us the means of deducing this initial state, rather is by showing that it was never needed. We never needed to know this state. Okay?
Like, imagine a Stängerloch experiment. We have two devices, and we first measured it in x-axis and then y-axis. So, or 2 times x-axis. For the second times x-axis, since it was already been measured in the first time, then I know exactly what is the state.
You know what the probability will be 1.
If we have a full mixed state, I don't know if it's like a spin up, a spin down, it's 50-50%. Then I do the measurement, it collapses to one of those.
But you're racing now. You're introducing new elements, collapse. You just introduced collapse. We never talked about what is collapse. What is collapse?
Just suddenly one of the problems goes from something between 0 and 1 to 1. And the other ones, all of them go to 0.
What we have right now, we know that there is an evolution generated by Hamiltonian, and represented formally by unitary operators.
What is conditional probability? Like, if it is, I know that if I have already measured an x-axis, that I know exactly what will be the answer.
Yeah, so you know that the probability will be 1.
Exactly.
Surety. Or 0, depending on what you measure. I mean, probability that you measure the other result will be 0, would be 1. Yeah, sure. If there is no dynamics, okay. If there is no dynamics. Then what's wrong with that?
Because initialization, I need to know it was between x and y.
Oh, okay. So how do you using this construction, we can now maybe describe the experiment better to like illustrate what's going on. So this does not fully resolve issue of initialization yet. Okay, we will get there, but this is like a right step. So imagine that someone gives you a system, okay, and now you come in and you measure this y observable first, okay. Or maybe measure O, observable O, to get our the thing we did in the beginning. Now, if this result is something else than 0, okay, we abandon the experiment. Okay. If it is 0, okay, we continue. We wait for some time t for the t minus t0 to be more specific, and then we deploy the x device, and the probability that the result x will be measured, the small x will be measured, is given by this formula, this kind of formula. Okay, and this is how you handle the initialization. Okay, there is still we abandoned. What we are missing still that okay, we abandoned the experiment if it's not specifically zero. So then what next? I mean, how to handle this? Because we want to continue our experiment. We want to try again. What to do? We don't know yet. We will get there. But at no point
you're preparing your state in a way to be measured in an X device and give you value X by doing.
But how did you prepare your state?
How do you prepare?
At some point, you have to follow this protocol of abandoning. That's the point.
I have this information
From
that, first of all, if I measure it in the basis of O, it gives me the value of 0.
Yeah, but how when you're practically doing the experiment, how are you going to make sure? Because you have first you do it, and if you did not get the expected result, you throw out. Now he's pointing out that abandoning that the ones that we don't want, he's trying to include that and come up with a new model without throwing away that.
Yeah, because
because that's important. You cannot simply, because now you are really biased for your experiment, because just because that didn't give you the expected result, you are throwing it out, and then you are trying to continue to make sure that your theory fits the experiment in a way, right?
Yeah, I mean,
this kind of focusing on what is that you want to have 0, for example, because you want to have trials, right? You want to repeatedly. If you just accept whatever, then the next trial you will actually be doing like different kind of experiment if you accept not only 0, right? So if you want to control for what is the initial condition, you discard the non-zero results and start over somehow. But we don't know how to start over yet. But we know at least that to start at least once, or to try to start, we don't need to know the state, which we don't know how to actually know what it is. There are no tools here, and there never was. There is no, in standard quantum mechanics is also absent, of course. It's not like I'm just coming up with this.
So if I understand correctly your argument, till now, the way we know about the state of a system is through some numbers that we expect to get, and then we assign that state to that system. Well, that's how we usually, till now.
When you get to
this question, which is rarely you get to this question in standard course. Okay, so let me show you my hand here. Okay, we are adults. We can talk shit on some stuff, right? This is a problem which is typically the resolution of this problem is by coming up, and that Navid already pointed this out, with a collapse. Because in the absence of this kind of this analysis that we did here, where we identified the Born rule as some kind of conditional probability, where the condition and the effect are both measurements. Okay, so in absence of this, you have to somehow make the observer be able to manipulate what the state is of the system, so that it can be fed to the another observer or to the same observer. No. I'm using measuring devices here. Okay? But if you want to use the state, the concept of state still, because here we are not using states here. There are no states. But if you want
the eigenvalue of the states, like you say, it's big different. Eigenvalues are measuring devices.
Because he still didn't specify physically what is a state. He's relying on the device to define everything. So he's kind of staying away from defining a state.
But device is related to the state, like at least in my mind. What device is just
choose one of the
eigenstates.
Yeah, that's true. That's in your mind.
All
I think.
The states in the Hilbert.
Yeah, like even
in your mind, you have to release. You have to open your mind. This is if you want to. This is something you have. If you want to connect it with state, right? To do it. To try to make something that, at least on the first glance, looks kind of consistent, although not really, you have to invent this physical process or maybe not physical, maybe it's formal process of collapse, where the measurement, where the measurement is concluded, you say the state of the system is set to something dependent on what observer saw by unknown mechanism.
Probabilistic mechanism. It's known, but it's probabilistic.
No, it's still unknown.
I mean,
it's still unknown. It's a feeling that you
but
have,
if you do measurements,
associating
you get like probabilistically this time, like because of the coefficient of the state is just not eigenvalues. It's just a probabilistic way to describe.
If you treat this construction, and if you pull it out of this context of just some series of measurements, okay, we'll get to sequential measurements, then it will be more clear. If you pull it out, if you really want to treat it as some physical process, if you choose to treat it like that, that is say, when the measurement is concluded, you don't know what measurement is because it's a primitive notion, measuring devices. It's not, I mean, you might try to model it later on, but if you choose to believe that this collapse happens, okay, to this, and it modifies the state, then you assume that this is some physical process that occurs objectively, right? And now you want to, okay, so how does it look like? Let's Wigner-Friend scenario. Let's try to model this in some way. And this is basically how you infinite factory of paradoxes, starting with EPR, Einstein-Podolsky-Rosen.
It's basically the measurement problem in quantum mechanics. You're walking around
the measurement problem, for me, like is to model measuring devices and to justify Born rule, let's say. If you introduce collapse, you're making your measurement problem extra spicy, extra difficult, because you very quickly realize that, for example, this collapse, if it's supposed to work like wanted, it cannot be modeled with any quantum dynamical laws. No unitary evolution operator can model this. It's impossible because it's strictly non-unitary transformation. So we have to come up with something extra, something that's not quantum dynamical laws. And then it's okay, so what is it? Maybe it's happened when the conscious beings are doing the measurement in some way, when there is some magical extra process that happened. But how exactly it happens? Because if you are not specific how it happens, how much time it takes, is it like objective or not, you cannot answer the Wigner-Friend question. And when you try to model it in some way, I guarantee you that people try different things, and I guarantee there is always a paradox there, because it's not real. Because it's not real. This collapse, idea of collapse, comes in if you insist of making this connection. If you insist on keeping the state as basically the master object of your formalism, which is not necessary.
For example, it's conditional. Probability for me is just reducing the Hilbert space to a subspace that like satisfy your condition.
But how do you, but you characterize it through the values. That's what I think is the point. You only get value numbers in experiment.
This reducement is called measurement, like one measurement and then.
No. This is okay. Very good. This is a pivotal error we are making. You said, okay, you describe what formally happens with those operators, what they are doing.
Yes, exactly.
But you said that projection. But you said, so this projection is the measurement. No, you have no reason to say that. You say measurement, some kind of measurement, can be modeled with this mathematical expression. This is a way to describe measurement. It is not, it's a representation of measurement. It's not measurement itself. This is one way of writing it down in your formalism. It doesn't. No.
Because you are not accounting for the actual process of measurement. You are only modeling what happens during, like not even that. It's like you're somehow.
Let me explain what is the difference. I can write down basically everything I want. I can do some crazy inscriptions here, whatever. As long as it's like legal mathematical operation, I can write whatever I want. But only very few of those expressions I can write actually have interpretation. They mean anything outside of some shenanigans. Yes?
Do you mean there is no measurement in this formula? There is no notion of...
No. This formula represents measurement, but the formula is not the measurement itself.
It's not capturing the physical process of measurement.
Yeah, it's kind of like a model. No, represent. No. And also, interpretation. So you have mathematical expression. Interpretation connects it with some phenomena, let's say, but it does not mean that this either the mathematical formula nor the interpretation is the phenomena itself. Okay, do you understand? In other words, there is a possibility to describe the same phenomena in different set of formalisms, different set of interpretations, and stuff like that. Okay, it's not like mathematics.
It's like probability. See, if you assume a probability distribution for some physical process, that itself does not tell you anything about the underlying process. There's a difference, but you can still capture the experimental numbers that you are getting, but that probability itself need not tell you about the underlying mechanism. That's what kind of is hinting at. Yeah.
We are using projection operators to describe measurements here, but not all instances when you write down some projection operator, because it can appear, you can like rewrite almost every formula to involve some kind of projection operator. This does not give you a permission to say, oh, because there is a projector in some formula, this means that there is measurement involved. No. There are some contexts where you want to describe measurement, a physical process, or any other physical process, and you do it on the formal side, you do it with formulas that have some elements like projection operators, okay? But not all appearances of projection operators automatically mean that the thing described by those formulas involve measurements, okay? It's like the model is not the thing that it models, you know? Model is a model, thing is the thing. It's like if you imagine something, doesn't mean that it exists.
You don't separate these pieces.
For me, it's Schengela. No. It's telling me if the Sx is +1, measure xy. Like if we get this eigenvalue for x-axis, go for sy.
Yeah, this is what it tells you.
So projection means measurement.
No.
At least in this, I don't know.
You must leave the space and just keep this.
You need to do measurement for that. Okay.
Navid, look at this. Look at this, my guy. Look at this, my guy. Let me find some projection operator.
Yes, measurement.
Why?
Observable, OX.
But again, it's not associated with any physical process. It's our feeling that it's the measurement. If you started with this mathematical concept, no student would ask, is this measurement?
Do you remember
it's not obvious from the math.
Do you remember how we constructed this? We started. Okay, there's Bone rule, which someone emailed it to us, and there was a projection operator. Okay, this formula supposedly describes the probability of measuring something, and you do measuring device. We have all the story about measuring devices and stuff like that. And there were projection operators there. And then I said, oh, look, instead of like keeping all those set of operators, set of eigenvalues or numbers, the spectrum, I can like pack them into one object. So I pack them into one object. This is like a way to store information. It is connected in a certain way to measurements, right? But it's this x hat equals blah, blah, blah. It's not even describing any measurement happening, that will happen, or whatever. We discovered x actually appeared in the expectation value.
This means mapping from the space that you're working to a subspace which can be described by measurement. Isn't it?
No, I don't. No.
That's just a map. Measurement is just a map.
problem.
From where to where?
Yes, from the space to a smaller subspace.
More fundamental.
Yeah.
It's like
They call it measurement problem.
You
Just do it.
you cannot describe Hilbert space operator representation with measurement. You cannot describe it using that. How?
The question of whether you associate this with measurement, I think that's the issue.
There's
This association, that feeling of measurement being associated with projection, that's the question here, whether that's correct or not, or is there a better way of
It's
thinking of it?
working. Like so at least even
No,
you say
it's
you
not
say
working.
sometimes
Like,
sometimes
No.
it works. You said that
Sometimes.
it works.
Then it means that
We'll get to the context where it stops working. Explicitly stops working.
So, for example, in the measurement that you said, like you measure x first and y first, for example, I would like simple question, what happens during the time in between? Like for example, you cannot make perfectly simultaneous measurements, right? So there will always be a delta t between the
that's
two
engineering
measurements. So,
question
but this is, at least for me, I don't see that this effect being captured there.
That you're right, but I'm not.
So,
No. This is fine. This is no. Don't feel. This is a classic error that people make all the time. Where you're so used to doing physics in this way that you don't have this distinction. I mean, used to. This is basically how they teach us this. You don't make this philosophical distinction between formalism and interpretation, how they come in, how they mesh together, how they are like movable and malleable. That you're basically forced into this mindset where you identify some mathematical objects with the things that those objects model or are part of models. This is basically you have to train yourself to unlearn this, okay? Because they are teaching. This is how we are taught this. And this is like automatically you just absorb it. But so you have to like train yourself to resist it. Basically see, okay, there are distinctions. What is model? These are philosophical questions, right? Of course. So we have have tools to handle philosophical questions. They don't give those to us. You have to find them on your own and apply them on your own without guidance, basically. I mean, I'm here. I'm guiding you now. I'm not doing maybe the best job, but this is a big, humongous, gaping black hole in the way physics is taught to people. That we have no philosophical tools. So things like model is not the phenomena it models. It just sounds like gibberish to you, right? But for me, it's perfectly. I spit those things like it's just the natural thing for me to think about. But because I spend a lot of time reading and learning, bashing my head in the wall to basically relearn this stuff. I'm sure that for like a philosopher, this is like basic stuff, very simple, the kindergarten stuff. But for us, because the way we are taught, this is like, oh my God, this is like mind-blowing, completely new. Oh my God, just because we are dumb, basically. illiterate and dumb as a physicist. So it requires effort to make this, to make this like to see that there is something going on here that makes sense. It's not random. Okay, but this is one of the key steps is to realize that formal mathematical expressions are in one bucket. They are on their own. They are meaningless. The meaning only comes from interpretation. But interpretation, not every mathematical expression you can come up with has and requires interpretation. Most of them don't. So you cannot make this mistake because it is an error. It's logical fallacy, logical error. That because some formal elements are in some formula that has interpretation, that this automatically means that those formal elements on their own also have some kind of interpretation. Okay, the Born rule as a whole has an interpretation, or this conditional probability, which is basically a way to rewrite Born rule. As a whole, it has an interpretation, but the things under the trace, they don't have any interpretation. Okay. If you start to believe that they do, I mean, first of all, there's like no logical reason to think that. But if you try to, you will be led astray. You will be doing some, collapse is a real thing. Here's my modifications to quantum mechanics to introduce some additional stochastic elements to have a like objective collapse. And I don't know what objective is because I don't know philosophy and I don't know stochastic processes as well. But whatever, man, let's do it because it's a process to understand it, okay? But we will get eventually. Okay, sorry. We will get to the quite rapidly next lecture to the place where it will be more clear that this. It will be more clear. Sequential measurement, basically. Okay. I'm sorry. I'm sorry. Stop me when we are so overboard. Okay, so yeah, let's finish this for today.